So I want to talk about basically one problem and its solution. But the reason it fits into the general theme of this workshop is that the notion of quasi-randomness occurs very naturally in the solution of the problem. So let me start by saying what the problem is. And it's a question that was asked by Babai and Shosh. They asked the following. Can you find a positive constant C such that for every finite group there's a, well, I'll say it quickly, there's a dense product-free set. So what I mean by that is you can find some subset A of G such that the density of A is at least C in G, and you can't find any product of two elements of A that also belongs to A. So that's what it means to say that the set A is product-free. So a quick remark to make about this is that for abelian groups, the answer is yes. To see that, first of all, just notice that if you've got a cyclic group, the answer is yes, because if you think of a cyclic group as arranged in a circle, if you take the outer third of that circle, sorry, let's go the other way around. So we'll have the identity here, and the outer third will be over here. If I take a product of two elements in the outer third, then they won't belong to the outer third, and so we have a set of density a third. Maybe there's a slight problem if the size of the cyclic group is tiny, but basically it's roughly a third. And because every abelian group is a product of cyclic groups, it's easy to extend that to all abelian groups. So it's clear that if the answer is to be no, there isn't such a constant, then you need to look at groups that are non-abelian. It would make sense to look for groups that are as non-abelian as possible in some sense, and we'll come back to that. I would say that the general expectation of this problem was that the answer should not be yes, unless you could find some trivial reason for always being able to find a dense product-free set. Then it sort of seemed as though there shouldn't necessarily be one in every group. And so really the question was not what the answer was going to be. The answer I'll say right away, the answer is no, there doesn't exist such a constant C. And the question is how to prove that. So I didn't write it down, so let me just say this was a question of Babai and Shosh. Another small remark is that one might as well confine one's attention to simple groups. And the reason for that is itself simple. So supposing G has a normal subgroup H, a non-trivial normal subgroup. Perhaps I won't even bother to write anything down. Supposing in the quotient of G over H, you can find some large product-free set, then you just take those cosets in G, and they form a large product-free set in G. So a large product-free set in G over H implies a large product-free set in G. Conversely, if you have no, contrapositively, I mean, if you have no large product-free set in G, then you have no large product-free set in G over H. So you might as well just keep quotienting by normal subgroups until you end up with something simple. So if the answer is no, then it is no for some simple group. Now this is typical asymptotic speak. One always has to make this little apology. Of course, for any fixed simple group, the answer is you could just take some element that's not equal to the identity and then define C to be 1 over the size of the group. So of course what I really mean is some infinite family of simple groups. It turns out, in fact, that any family of simple groups will do, but that's another matter. So the first sort of thing to do is to say, well, let's see if we can think of some fairly nice family of simple groups. And I will just, as I say, it doesn't actually matter what you choose, but here is quite a nice choice. It's PSL2Q. I don't really know exactly what expertise I should assume, so I think I'm going to err on the side of telling people things that they know extremely well. Therefore, I will just quickly say what PSL2Q is. You take SL2Q. I won't say what SL2Q is. You take SL2Q and you quotient out by the subgroup that consists of the identity and minus the identity. And that produces for you a simple group. So it's 2 by 2 matrices, but each matrix is equivalent to minus itself. And they should have determinant 1. So this was just a nice family of groups because you've got 2 by 2 matrices. You can sort of think of them fairly concretely and so on. Now, another thing to think about is how is one actually going to prove that A is product-free? So we've got another way of thinking about showing that A is product-free is to say if I take the product set of A with itself, it should have an empty intersection with A. So we could think what's going to cause this never to happen? So what's going to cause, let's put a not there. What is going to cause the product set of A with itself always to have a non-empty intersection with A? Well, the most basic possible way that might happen would be if the product set of A with itself was always very large. So supposing I knew that for some C equals Cn tending to 0, so C is no longer a constant but just something that, some function of n. Supposing I knew that whenever A has density at least C, that implies the product set of A with itself has density at least 1 minus C, sorry, greater than 1 minus C, then that would certainly imply that the product set had a non-empty intersection with the original set. And once you've thought of doing it this way, then a natural further thing to think is, well, perhaps it's not so important that we take the product set of a set with itself and want it to have a non-empty intersection. Well, now already I don't really care that this set A here is A rather than just any old set of cardinality C times, or density C. So if I don't mind this being, whether this is the same as these two, well, do I even care whether these two are the same as each other? Perhaps I don't. So a natural generalization that one might think of for this problem is to say, in fact, perhaps if I just take any reasonably large set A, any reasonably large set B, take the product of those two sets, I'll get something that fills up almost all the groups, so there just isn't room for another set C. And that again, well, that turns out to be the case. So what I'm actually going to show is that it's what you might call an off-diagonal version of this problem. So it says that if A, B, and C are any reasonably large sets, then you can always find x in A, y in B, and z in C such that xy equals z. Or to put it another way, the product set of A and B is not disjoint from C. And there's one further remark to make that brings in quasi-randomness, which is this. How's one going to show that a product set fills up almost all the group. Well, if you've done any additive combinatorics and looked at sum sets and things, then there's a very, very standard answer to this sort of thing, which is that you define, so actually, well, I was going to say I'm going to be doing products of two sets. So I'm assuming that A and B are reasonably large. I want to show that AB fills up almost all the group. The standard way of doing this is to say, well, let's define the convolution A star B. Now, I would normally define this in a slightly different way from the way I'm doing it now, but I'm going to, so we'll define A star B of G equals the number of ways of writing G equals xy with x in A, y in B. So normally I would divide this by the cardinality of G, but I think I'm not going to do that for this talk. So it's really a convolution of the characteristic function of A and the characteristic function of B, which I like to write as just A and B. So if we want to show that AB fills up almost all the group, one way of doing that is to show that this convolution is roughly constant. And if it's roughly constant, it can't be zero too much of the time. And the sense of roughly constant is that it should have small variance. So standard method of attack show that A star B has small variance. You have to work out exactly what you mean by small, but that's not so hard. Actually, I'm not quite really going to do that, but I just mentioned that to tie it in a little bit with other notions of quasi-randomness. Now, another step that I'm going to take, which it's a small reformulation of the problem that you don't actually have to do, but I think it's quite nice to do, which is to express it in terms of graphs. So associated with a subset of a group, one can always define a Cayley graph, at least if the subset is symmetric. In this particular case, there's nothing telling us that A is symmetric in the group. One could study the problem where we just add the extra assumption that A is symmetric, but we haven't got that here. So what I want to do is define something that's more or less a Cayley graph, but it's a sort of non-symmetric Cayley graph, or what I would think of as a bipartite Cayley graph. Because I've got G as the group, I'm going to have to call the graph gamma. So gamma has vertex sets G1 and G2, and those are both just copies of the group G, and we'll join x in G1 to y in G2 if and only if there exists A in A such that AX equals Y. So that's a sort of, as I say, a sort of bipartite version of a Cayley graph. Equivalently, we want y x to the minus 1 belongs to A. I'll stick it up there. Now, once you've got a bipartite graph, you've also got a matrix. So the matrix takes a function defined on the first vertex set and will give you a function defined on the second vertex set. Just for convenience, I want to write down precisely what that function is. So if I've got a function f from G1 to R, then let's write alpha for the linear operator associated with the matrix that I get from A, or the graph. So alpha f of y is going to be sigma x a of yx to the minus 1 f. Well, since I've written it like that with a suffix, I'm going to do that. So a of yx to the minus 1, I'm sort of using the letter for all sorts of different things. So a is the characteristic function of the set. So I just sum over all x, a 1 if yx to the minus 1 belongs to a, and a 0 otherwise of f of x. Okay. Now, we have to think how we can get a handle on alpha. So what we really want to do is to show that alpha has the following property. If it takes any sort of function defined on, this should be g1 and g2. It should take any function on g1 and somehow sort of smear it out in a nice way. So the function defined on g1, I should say also that alpha of the characteristic function of b just is a star b. So this linear map is working out the convolution with the set A as defined before. So what we want is for this linear map to take functions and make them more or less constant. So another way of thinking about that, if you're in a L2 frame of mind, is that it should look at the subspace that's orthogonal to the constant functions and take everything in that subspace and make it much smaller. So that's what we would like to prove. We'd like to prove that the norm of alpha, when restricted to the space of functions that are orthogonal to the constant functions, is quite small. So the next question is how we get a handle on the norm of alpha restricted to that subspace. And for that purpose, we'll use the singular value decomposition of alpha. So this is maybe extremely familiar to some people and not to others. So I'll just take a tiny bit of time out to talk about singular value decompositions. So if you've got a symmetric matrix, then I like to say the following, that A equals sigma lambda I ui tensor ui, where the lambda i's are the eigenvalues and the ui's are an orthonormal basis of eigenvectors. All right, perhaps I should just say some random matrix, sorry, not random matrix, but some arbitrary matrix. Thank you, S, all right, that'll do, yes. So this is the case that we're not talking about, so to speak. What do I mean by this notation? I mean the matrix whose x-yth entry is uix, uiy. And if you want to convince yourself that this, again, I'm not sure I really need to say this, but anyway, if you want to convince yourself of this equality, just apply it to one of the eigenvectors ui, and you find that you do indeed get lambda I times ui. And therefore, by linearity, the matrix really is what it's supposed to be. But we don't have a symmetric matrix, so what can we do instead? So and the answer is we can do something very, very similar, except that instead of ui here, we have to say vi. Now, what is the precise claim? The precise claim is that given any matrix, you can find a decomposition of this form where the ui's form an orthonormal basis of the first space and the vi's form an orthonormal basis of the second space. So it's a bit like eigenvectors, except that because it's not symmetric, you really can't expect the ui to be the same as the vi. But apart from that, everything goes through. And actually, all the things that you can say with eigenvectors and eigenvalues, or most of them, have very natural counterparts for singular values. Let me just quickly establish that the singular value decomposition exists, or I'll sketch an argument.
Does it mean alpha, not A?
I see what you mean. Well, okay. Basically,
You call it, I mean, it's the same thing, but you call it alpha before the operator.
well, alpha was the map, and this was the matrix somehow. So I feel sort of uneasy about using alpha here. I don't really care about it much, but I feel slightly uneasy about using that because I feel as though this is a matrix and alpha is a linear map. But on the other hand, since A is already a set and the characteristic function of that set, perhaps those considerations outweigh my small uneasiness. So I feel myself outvoted. The problem, actually, I'll tell you why I'm trying to be economical with notation. It's because I also really wanted to use alpha for the density of the set A. But I got real problems. Yeah. Actually, I'm going to use little a later on for the density of A, which I don't like, but that's why I've chosen typical elements of A to be x, because otherwise that would interfere with my wish for A to be the density of A later on. So it's just, I don't know, yeah. There are just too many things associated with the set A, unfortunately, in this. So a very, very quick sketch of why the singular value decomposition exists. The proof I quite like is that you can, there are algebraic proofs of this, but I quite like the following analytic proof, that you start by picking V, a unit vector V. So I'll just have a new board for this, actually. Such that alpha V, that's the L2 norm, is maximized. Now I claim that if W is perpendicular to V, then alpha W is perpendicular to alpha V. And the reason is that if not, we can build some other vector where the norm, another sort of unit vector where the norm is bigger. And the way we do that, we just look at V plus delta W for some very small delta. Now, if W is perpendicular to V, then the norm of V plus delta W is 1 because V was a unit vector plus big O of delta squared, whereas the norm of alpha V plus alpha delta W, let me just square it for the calculation, so that's alpha V plus delta alpha W, alpha V plus delta alpha W, equals alpha V squared plus 2 delta alpha V alpha W plus little o delta squared. And then this thing here, if alpha V alpha W is not 0, we can make big by choosing delta to be small and positive or small and negative according to whether this is positive or negative. So that we can make the norm of alpha V significant, or alpha V plus delta W significantly bigger than the norm of alpha V, whereas just the norm of V plus delta W is not significantly bigger than the norm of V. So that would be a contradiction. Therefore, we're done, because we now know that alpha maps the space of things perpendicular to V to the space of things perpendicular to alpha V. So we can just, by induction, we can decompose everything else. In our case, we know that alpha is a matrix that's coming from a regular graph, and from that it's easy to prove that, which I won't do here, but it's easy to prove that the vector V that maximizes or gives us the first singular value, just as you get in quasi-random cases and eigenvalues of graphs, is a constant vector. So let's say alpha v, let's write this fact down, is maximized when v is a constant vector. And it's assuming the graph is connected, that's the unique maximizing thing. So here I'm making an assumption. This is not for an arbitrary, arbitrary linear map alpha. That's in our particular case when alpha comes from a regular graph. And indeed, in that particular case, alpha v will also be a constant vector. So a small fact that we'll need later on is that because of this, alpha will take, well, actually you can prove this directly as well. Alpha takes something that's orthogonal to a constant vector to something else that's orthogonal to a constant vector. Right. Still haven't said anything about PSL2Q and where that comes in. That comes in at a late stage. And as a matter of fact, we shall just use one fact about PSL2Q, and we'll use it as a bit of a black box. So now, the rough strategy for the rest of the proof is this. We know we've got a singular value decomposition. What we'd like to show is that, so we know that lambda 1 is actually the cardinality of the set A. That's because if you take the constant vector of 1s, then each 1 here contributes a 1 up on the other side for every single element of A, and therefore you get the size of A times your constant vector 1 when you apply alpha. What we'd like to prove is that we want lambda 2 to be small. So this is the bipartite version of wanting the second eigenvalue to be small. So why do we want lambda 2 to be small? Because lambda 2 is telling us the norm of the operator when it's restricted to vectors that are orthogonal to the constant vectors, and that's what we want to be small. So if lambda 2 is small, we're basically going to be done. And the strategy for proving that lambda 2 is small is a very nice trick that's been used in a number of situations by various people, which is to show that because we're in a nice sort of group situation, lambda 2 has to occur with fairly high multiplicity. Now, if lambda 2 has to occur with high multiplicity, and we also can say, and I'll do this in a moment, we can say what the sum of the lambda I squareds is, then the only way that can happen is if lambda 2 is reasonably small. So, so let's quickly prove something very elementary about the size of the lambda I squareds. So notational problems again, but let's write alpha xy for the xyth entry of the matrix. It actually turns out to be, when you work it out carefully, sigma lambda I ui y vix, that way round. So before I wrote, in the symmetric case, I wrote uix uiy. That was okay because ui equals ui, but here I've got to be slightly more careful. So now let's work out what does, what I claim is that the sum of the lambda I squareds is actually the number of edges in our graph. This is again something that happens very much in the normal case with symmetric graphs and eigenvectors and eigenvalues. Let me just very quickly do that as well. So sigma alpha x y squared is sigma x y sigma lambda. Well, I'll do this in two. So I'll do this in one step. So I'll sum over ij I lambda j ui y vi x uj y vj x. And if I interchange the summations and take the lambda I lambda j out, we see that summing over x, I've got vi x vj x, and with the y, I've got ui y uj y. So I end up with sum ij lambda I lambda j vi vj ui uj, and that's just a delta ij. That's another delta ij. So this is sum I lambda I squared. So this, as in the case of graphs or symmetric matrices, the sum of the eigenvalues is the Hilbert-Schmidt norm of the matrix, which, when the matrix is just zeros and ones, tells you how many ones there are. Right, I think we can afford to remove these preliminary remarks. And even the statement of the problem. So that proves that the sum of the lambda I squareds is not huge. Actually, what is this side over here? It's just, I think I'm going to call the size of G n from now on, rather than writing the size of G all the time. So this gives us n. That's the number of vertices on one side, and then the number of edges out of each vertex is the size of A. So we get n times the size of A. So the sum of the squares of the singular values is n times the size of the set A. Maybe it's an appropriate moment to say that to make much more explicit, I think it should be fairly clear, but let me be completely explicit about where quasi-randomness comes into all this. So we're trying to prove that this bipartite graph, this sort of bipartite Cayley graph, is quasi-random. In a loose sense, that it'll sort of behave like a random graph. And there are various different ways in which random graphs behave. One of them is having random bipartite graphs, let's say. One of them is having a rather small second largest singular value. Another is let's put the following are equivalent for a bipartite graph with vertex sets of size n. Let's call them x and y. I'll do a simple case, but you don't actually need to assume this regularity, but it sort of makes things a bit nicer. That's regular of degree Pn. So what the name of the game here is to find properties that will make the graph behave like a random graph with edge probability P. And so one of them is lambda 2 is little o of n. Here I'm going to assume that P is some fixed constant and n tends to infinity, but actually if you do the calculations carefully, you can let P tend to 0 as n tends to infinity, and that's what we'll actually need later on. But I'm just going to state it in the regime where P is some fixed constant. So one is that the second largest singular value is not too big. Another is that the number of labeled 4 cycles x1, y1, x2, y2. So in G. So by this I mean that x1, y1 is an edge, x2, y1 is an edge, x2, y2 is an edge, and x1, y2 is an edge. That should be what you get in a random graph, or what you expect in a random graph, namely p to the fourth, n to the fourth. So why do you expect p to the fourth, n to the fourth? Because there are n ways of choosing each of these four things, and then each of the edges, each of the four edges has a probability p of belonging to the graph, plus some small error, which we can write as little o, n to the fourth. So the error term just has to be significantly smaller than the main term for it to count as quasi-random. By the way, the proof that these two are roughly the same just goes by using an argument very similar to that to show that the number of labeled four cycles is the sum of the fourth powers of the singular values. And again, this has, well, it's obvious in a way that everything I say for singular values is going to have a counterpart in the eigenvalues case, because the eigenvalues just are the singular values when the matrix is symmetric. And the third one is that if, well, let's call it B and C, so it ties in with what we'll do later on. If B is in X, C is in Y, B equals Bn, C equals Cn, then the number of edges from B to C is what you'd expect. So what you'd expect is we've got BCn squared opportunities to have an edge. Each one has a probability p of actually being an edge. And then we have our little error term. So we have three properties. One is a small second largest singular value. Another is the number of labeled four cycles. Actually, it's easy to prove that the number of labeled four cycles is at least as big as this, and so using Cauchy-Schwarz. So what this is saying is that the number of labeled four cycles is as small as you can get. And then here we're saying that between any two reasonably large sets, you get roughly the expected number of edges. There are several other properties that I could write down, but we may hear more about those in the next talk, so I shall leave it there. Except I want to make one remark, which is a remark about why quasi-randomness is useful. So, I mean, I could talk about this for a long time, but a sort of brief reason for quasi-randomness being useful is that it shows that something that looks sort of very much first-order local sort of property is equivalent to something that looks much more like a second-order global thing. So here we're quantifying over some small structure, or we could say we're quantifying over x1, y1, x2, and y2. So that's what I mean by a sort of first-order thing that looks for some tiny little structure. Here, we're quantifying over all subsets of x and y. So it often happens that you know, it's sort of easier to prove something about the sort of local structure, and then from that you can deduce something about the global structure. Often the way things work is that you're trying to find some small configuration. If you can't find some small configuration, it proves that the graph is not quasi-random. That gives you some massive global statement about two sort of huge sets that misbehave in some way. And that's going to be precisely, well, it's going to be sort of semi-precisely where we come in. So the local global thing, I'm not sure quite how to fit eigenvalues into that. They sort of seem like reasonably global things, but somehow they're amongst the easier things to check. So I'm not quite sure what to say there as far as general remarks are concerned. But nevertheless, we are still doing the useful thing of we're going to prove something about, we're going to obtain the quasi-randomness via one condition, but we're going to apply it via another condition. So it's just, it's useful in the way that all equivalences are useful, that sometimes it's nice to be able to prove one thing and then apply another one. But it just happens to come up rather a lot. A quick remark about quasi-random graphs versus expanders. So there are various sort of similarities and various differences. So one obvious similarity is that the second largest singular value or second largest eigenvalue crops up in both. Another is that if you've got a really good expander, it looks fairly random in some nice ways. This third condition looks very similar in both situations. But expanders tend to be where the degree is some fixed constant and n is tending to infinity, whereas here the degree is right at the other end of the scale usually. The degree is some constant times n. The second criterion there about the number of labeled 4 cycles is not something that would make sense in an expander context. The only labeled 4 cycles you get in an expander typically will just be degenerate ones that hop up and down an edge. Another thing is that with expanders, for many applications, you're just happy if there is some spectral gap. You know, the second largest eigenvalue doesn't have to be small, it just has to be decently smaller than the top eigenvalue, whereas for quasi-randomness, we definitely like the second eigenvalue to be little o of the largest one. So on the other hand, we don't ask for sort of Ramanujan. Normally with quasi-random graphs, we don't ask for them to be as quasi-random as possible. We're satisfied typically just as long as the error term is little o of the main term. So there are various sort of slight differences in the way the two notions are applied. And okay, so let's now prove a rather simple but very important lemma. So now the key thing we want to prove is that the multiplicity of lambda 2 is high. So first of all, I want to make I'll do it in a series of very simple claims. So claim the set of V such that alpha V equals lambda 2 of V, or equals lambda 2 times the norm of V, is a subspace. The way to see this is sort of, I'm not going to call this a proof exactly, but the reason is it's the subset of vectors orthogonal to 1 for which alpha V over V is maximized. So it's obvious from the singular value decomposition. So why is it obvious from singular value decomposition? We know that alpha of Vi equals alpha of Ui equals lambda I of Vi. And the Ui's and the Vi's are orthonormal bases. If you're not allowed to use U1, then if you want the norm of the image to be lambda 2 times, I'm assuming that we've got lambda 1 greater than or equal to lambda 2 greater than or equal to, let's suppose we have the following situation, actually, be a little bit more precise. So we've got lambda 1 greater than lambda 2 equals lambda 3 equals up to lambda k greater than lambda k plus 1 greater than or equal to, and so on. Then if you want a vector that whose image has norm lambda 2 times the vector itself, it had better be generated by, and it's orthogonal to the u1, then it had better be generated by u2 up to uk, because otherwise we're going to sort of waste some norm over here. So, I beg your pardon?
In the claim you assume V orthogonal becomes.
Oh yes, I beg your pardon, yes. Yes, absolutely, yes. Otherwise my proof breaks down, but that's what I need, yes. Because it's, thank you very much. And so the next thing, so we've got a subspace. So what I want to prove now, and I'll say why I want to do this as well, but I want to prove that this is very simple, that G actually acts on this subspace. So if G acts on this subspace, that proves that the group G has a representation of dimension equal to this subspace, or at most equal to this subspace. And it just happens to be a nice fact about PSL2Q that it doesn't have any small dimensional non-trivial representations. Therefore, the subspace must have high dimension. Therefore, lambda 2 occurs with high multiplicity. So that's roughly how the proof's going to go. So once I've proved that G acts on this subspace, we'll be more or less through. Well, let's just remind ourselves, I hope I've still got it there, what the matrix was. Yes, it's up there. So the way I'll make G act on vectors is I'll define, for H in G, I'll have TH of V of G is V of GH, so I'll have multiplication from the right like that. So if I apply one of these operators TH to V, then all I'm doing is permuting the coordinates of V, so it obviously preserves the L2 norm of V, and we can just check that it also permutes the coordinates of alpha of V. So let's just do that. So alpha TH of V G is, right, I seem to be using, let's call it X, so I can conform with the notation up there. So it's going to be, let's call it Y actually. So sigma X of A yx to the minus 1 V xh. Now, very sort of, I have a colleague in Cambridge who calls this sort of argument baby representation theory. So it's sort of the representation theory that you do in the first 5 minutes after being told the definition of a representation. So we can just rewrite this as sum x a yh xh to the minus 1 v xh. And now we can substitute z equals xh. So that's sum z a yh z vz, which is precisely alpha v evaluated at yh. And so therefore, alpha of thv is just a rearrangement of alpha of v as well. So both the norm of v is preserved when you do th, and the norm of alpha v is preserved when you do th. And so therefore, the ratio is preserved, and therefore G is indeed acting on this subspace. I should also say it's acting non-trivially on the subspace. That's not hard to check, that it's not just the identity everywhere. So we have a non-trivial representation of dimension. The way I've written it here, I suppose it's k minus 1. But now let's just, what is the fact I want to use about PSL2Q? The smallest non-trivial representation of PSL2Q has dimension q minus 1 over 2. Well, what's the size of the group? Well, very roughly speaking, once you know 3 entries of the matrix, it determines the fourth. That's a slight oversimplification, but anyway, it's roughly q cubed. So what this is saying is if the group has size n, then there's no representations of size smaller than, I better not call it c, had I, theta n cube root. So, and that's a pretty remarkable property, really, that you can't find. That's pretty big for the size of the smallest possible non-trivial representation. And the reason I say this proof works for all simple groups is that all we need for the proof to work is that the size of the smallest, or the dimension of the smallest non-trivial representation should tend to infinity with the size of the group. That's true for all simple groups. But it grows much more slowly for some. So for example, for an, it grows more like log n. Also, log of the size of the, it grows more like n. I think it's n minus 1, which is, well, it's not even quite logarithmic in the size of the group, although it almost is. Well, just a tiny little exercise to finish off at this stage, but I think I will do it. So, I mean, why are we more or less done? Because we've got that the multiplicity of lambda 2 is big. Well, let's just see exactly what that tells us. So, we know that sigma lambda I squared equals n times the size of A. But we also know that it's at least as big as theta n cube root of n times lambda 2 squared, because lambda 2 squared occurs with multiplicity theta n cubed. So that's less than or equal to n times the size of A. So that gives us that lambda 2 is less than or equal to, that's n to the 2 I made a mistake. That doesn't look quite as I remembered it looking. But just want to check that while that's 2/3. Yeah, maybe that's okay. Just slightly embarrassing if at the very end it doesn't quite work out. But I think this is all right. So that tells us that any function that's orthogonal to the constant functions, when we apply the matrix alpha, its norm will increase by at most that amount. So now let's just write down an expression for the number of edges between B and C. Perhaps I haven't said this completely explicitly either. So the number of edges between B and C just to remind you, is number of pairs y in B, z in C, such that there exists, or such that, well, let's just write it like that. There exists x in A. It's a slightly silly way of writing it, since there's only one candidate for what x could be, but anyway, such that xy equals z equals number of products xy equals z, x in A, y in B, z in C. We want to prove that this is non-zero, although we can get for free that it's actually quite a large number. But also the number of edges between B and C can be thought of as the inner product of alpha B with C. Or A star B inner product C. And what we'll do here is something that's been done once or twice already this week, which is we'll split this up into a main term that says what we expect to happen in the random case, and then the rest that we try to show is dwarfed by the main term, and therefore our expectations are confirmed. So to do that, we're going to split each of B and C up into a constant part and the part minus that constant part. So density of B will be little b, density of C will be little c. So I'll write this as alpha b minus alpha b plus alpha b times c minus c plus c, where I'm writing b for the constant vector, that's b everywhere, and c for the constant vector, that's c everywhere. And c minus c, because I've subtracted the density, is orthogonal to constant functions, so it's orthogonal to this constant function here. And alpha of a constant function is a constant function. This is orthogonal to a constant function, and this is a constant function, so that part of the, because alpha takes something that's orthogonal to a constant function to something that's orthogonal to a constant function, so this part of the inner product vanishes, and we just get alpha b minus alpha little b c minus c plus alpha b c. So this is the main term. What is this? Well, it's just the number of edges in the graph times little b times little c. So that's a n squared, because density of A is little a. So this is the size of A times n times B and C. So let's just write it nicely, A, B, C, n squared. Well, thinking of it in terms of the products, what you could say is, how many products do we get, or how many products do we expect to get in the random case? Well, we just look at, pick an arbitrary x and y, and the probability that x belongs to A, y belongs to B, and z belongs to C should be ABC. And there were n squared little events that we talked about there. So that's the main term. And then what about this? Well, the norm of alpha b minus little alpha b to this vector here is just a projection of alpha b itself, and this is just a projection of C. So we've got that the norm of this is at most the norm of the characteristic function of C, which is c to the half n to the half. I'm applying Cauchy-Schwarz to this, by the way. And the norm of b minus little b is at most b to the half n to the half. But we've applied the operator alpha. Because we know that b minus little b is orthogonal to constant functions, we know that we haven't increased its norm by more than what I had up there, theta to the minus a half. N cubed. Now, with any luck, oh yes, times a, that's useful as well. So I want an a to the half and another n to the half to deal with the size of capital A to the half. Now, it would be a total disaster if these powers of n added up to less than this power of n. But as it happens, we've got a half, a half, a half, plus a third. So we're in good shape. Let's just rearrange them. So we get ABC to the half. But what do we want? We want the main term to dominate the error term. So we want that to be a lot bigger than, well, let's just do a bit of cancellation. So that's ABC to the half n to the 1/6. That can get rid of all the powers of let's get rid of everything on the left-hand side. So we want that to be significantly bigger than that. So we need A, B, C to be a lot bigger than n to the minus a third. As long as that's the case, this term here dominates this term here, so we get lots of edges between B and C. So in particular, whoops, that was supposed to be an A. In particular, we could say that provided we got some reasonably large constant, provided we know that all of A, B, and C have size at least C n to the minus 1/9, then there must be a product with the first term in A, the second term in B, and the third term in C. So it's not just that the original conjecture was false, but actually the bound tends even quite fast to 0 as the size of the group goes to infinity. And as I say, there was nothing special about PSL2Q except that its smallest non-trivial representation happened to be particularly large, but any nice family of simple groups will work, or indeed any group with the property that it doesn't have any low-dimensional non-trivial representations. So the title of this talk, Quasi-random groups, that was a name that I gave just for the purposes of discussing this problem to groups that have this property, that there are no low-dimensional non-trivial representations. It doesn't really say that the group itself is in any sense random, but it just says that a lot of graphs that you can associate with it and function convolutions that you can do in it behave in ways that are rather like the way that random objects behave. And one final, I haven't quite used up my time as I thought I wouldn't, but one final remark I'd like to make is that if you just replace C by the set of inverses of points in C, then you can write it in a different way. You can say as long as A, B, and C are reasonably large, then the product set A, B, C is the whole of the group G. And in particular, again, you could set B equals C to be A. So in a quasi-random group, if you have a reasonably large set A, then its threefold product set has to be the whole group. And this is something that when people when people are looking at expansion in groups and looking at sets and asking how long it takes for a set when you take iterated product sets to fill up the whole group, this can be quite a useful lemma. It replaces other techniques that we used before, but it can be quite a useful lemma. It just tells you that once your set gets to be reasonably big, then at the next stage it has to fill up the whole group, or the next couple of stages. And there are other applications of this fact that I don't actually know enough group theory, as must be painfully clear, I think, but I don't know enough of group theory really to sort of understand why they're interesting. But I think sometimes even when A is a subgroup of a group G, it can be interesting to know that if you look at, so I don't mean a subgroup. What do I mean? I mean a conjugacy class, sorry. Sometimes when you've got a conjugacy class, it's quite interesting to know that when you multiply it by itself a few times, I think that's the statement. So I think maybe I will stop there because in the next talk there'll be a lot more about quasi-random graphs and quasi-random hypergraphs. Quasi-random graphs, this is a slightly perverse way of looking at them, are like quasi-random bipartite graphs, except that now the matrix is symmetric and things work out a bit more nicely. Although I would say that for many purposes, quasi-random bipartite graphs are actually rather useful in natural objects. For example, if you're looking at regularity lemmas, then as again you will have been talked about yesterday, it's really little bipartite graphs that you want to be quasi-random. So here's a nice little situation where quasi-randomness raised its head. And Avi said that if anyone wanted to ask questions, and there was a little bit of time, which officially there is, then I should do so. But so there is a small opportunity for that, if anyone wants.
So let's thank the speaker. Questions? Comments? Go ahead.
Is it obviously the case that this is not an if and only if, that that it's not the case that in any group that has very, very small representations, there is always some set.
Yeah, there are some.
It's a good idea to repeat the question.
Yeah, so the question was, what about the converse? So supposing you've got a group that has got a very low dimensional representation, is it then the case that you can construct a reasonably large product-free set? The answer is yes, but there's sort of qualitatively the answer is yes, but the bounds you get don't somehow correspond terribly well. So if you yeah, so the size of the product-free set that you get from your low-dimensional representation doesn't match terribly well the size that you don't get from the fact that that's the smallest one, so to speak. But yeah, there is an equivalence. So you can actually, because of that, you can draw up certain properties of groups that all turn out to be equivalent. So that's another way in which it makes it quite nice to talk about quasi-random groups.
Can you mention some of the other applications of this multiplicity trick?
Well, well, I don't really know them myself. I mean, do you mean other than when you're taking a set and expanding it and one?
Well, I know that there's a paper of Baba and Hilbert.
And Nicola?
Well, where they took this idea and applied it to other just basic group theoretic questions.
Yes. As I say, I'm slightly hazy on what precisely they did.
Basically, I think they were the ones to observe this, that ABC equals G, and also they replaced the half of the work of Elfgott by this argument, which made it so much easier. In Elfgott original work, he
had to work quite hard, even from once.
Yeah, even for the larger. I mean, he had the smallest set and the largest set was pretty hard, and using this it became almost trivial. Not trivial, but much easier.
But I think they did some other things that were not sort of little observations, but actually quite hard stuff, I think.
I think they gave Shallow's result about products of 3 words.
Maybe that.
The image of the word set is big enough so it satisfies.
Yes.
How long a lecture does one need to prove this fact about this PSL2 of G of Q?
How does one prove it?
No, how long?
How long is it proved?
Or if you can prove it right now.
No, I can't prove it right now. I've confessed that.
You just look at the Borel subgroup and you look, an element has Q minus 1 over 2 elements in it that are conjugate. And so it must have at least Q minus 1 over 2 distinct eigenvalues in any representation. So that's the proof.
Yeah.
So you're just even looking at the upper triangular subgroup of PSL2.
Mm-hmm.
It's already the Q band.
Now the question is, can you repeat the answer for the recording?
Oh, you really know how to sort of...
Well, maybe it's time for a coffee break. Let's thank the speaker and the audience.